Hey class. Okay, so sorry again for another late posted video. I was working on updating the notes to make sure that we could finish our background concepts. I will assign the first homework today. It'll be over Induction and Recursion. That's chapter 5 in your textbook. So if you hadn't started reading that after last week, then please start reading that material. I do have notes for chapter 5 in here, and hopefully that'll be sufficient to help you through your homework. But if you have any questions, let me know, and and we'll go over that on Thursday. Okay, so let's jump back into it. We will finish up the background concepts today. I will discuss briefly how to work with Overleaf, which will be the format that I'm recommending that you use for your homeworks. I give a 50-point bonus to students that submit their work, both the tex file, the .tex, and the PDF that is generated. And so I think it's a pretty good, a pretty decent bonus to at least attempt to do your work in it. I think the format is not so bad. It's typesetting, which I guess is it looks nothing like HTML, but the concept is very similar. So you're just formatting text, and you learn the lingo a little bit in terms of lists and so forth. Actually, now that I think about it, the language is distinct enough that maybe there's not as much overlap as I want there to be for this argument. But all the same, if you're ever going to do any kind of meaningful research, they'll expect you to generate PDFs using something very much like LaTeX. I provide you with the initial file, so that you're really just writing very simple paragraphs and formatted math. You can Google whatever help you need to kind of get you started. The ramp up time really shouldn't be too bad, and my hope is that the bonus makes it very much worth your time, so you don't really worry about your homework grade. It's with a reasonable amount of effort, you can expect to have over a 100 average on your homeworks. And then it'll also make, whenever we do the take-home exams, it'll make submitting them a little bit easier. But again, if you ever go on to do any kind of meaningful research, no one really expects that to be written in a doc, a Word, MS Word, or anything like that. I suppose it is possible, but it's not really the standard. So hopefully this will help you gain confidence as an undergraduate student for something that is a little bit requires a little bit of ramp up time for the typical grad student, as was my case. But it's not so bad. I'll help you get started. So we'll go over that at the end. But for now, let's jump into our discussion of networks, and then I believe we'll do hashing and encryption, and then I think source control management and automated builds. Yeah. Okay. All right. Let's get started. Okay. So networks. This was network security was my focus as an undergraduate software engineer, and so it can be incredibly complex, but the basic ideas of it doesn't have to really be all that difficult. As I note here, computers are great. They're wonderful. That's kind of what we're here to study, right? Is the computer and what can it do for us? But their real value is the fact that they can connect to other computers, and so I think it's worth taking a look at how that happens. What a little bit of the jargon that goes along with it to kind of demystify what's going on there, and then talk for a moment on hopefully as we go along, I will remember to tell you all how it is we can break these things and cheat and steal it and all of that stuff. Not so that I'm advocating doing it, but so that you understand where it is that you need to secure your data and what exactly it is that you can trust on a network, and perhaps what can be faked along the way. And hopefully that'll give you at least a little bit of intuition on network security as you go along. So, okay. So the first thing, you can't really talk about network communication without discussing TCP/IP. TCP, I don't even remember what the acronym stands for. I'm quite sure the P is protocol. The C is probably communication. T is maybe like transfer or something like that. I don't really remember. But it's not the only protocol. So there are four main protocols on that layer of the stack. And one of them is TCP, which is known as a form of reliable communication. The second one is UDP, which is unreliable data protocol, something like that. UDP. The third is ICMP, and the fourth is UGMP. Okay, so keep in mind that these protocols were defined, I imagine, probably back in the 70s or something like that, maybe the 80s. And it was at a time when they were still, making guesses as to how it was that these interconnected networks would play together. And so, TCP was imagined as this request-reply model where you would send a message and then you would get confirmation that it was received and that something was done with it, or an error happened on the other end, or whatever, right? But you would get some response. It wasn't just, fed into the ether. And so that is what's meant by reliable communication, is that you get some form of acknowledgement for whatever data it is that's sent. The unreliable model is something more akin to radio, right? So a radio station has no idea whether or not anyone is actually listening, unless they do some like call-in feature. Then they have no idea that anyone at all is listening to what's being broadcast. It's just sent out. Might be received, it might not be, and that's the idea of UDP. It turned out that wasn't really all that desirable of a protocol. There may be some something that I would consider obscure, right? But there may be some obscure services that use UDP. But if you imagine using it on the internet, this idea of something that's broadcast everywhere, well, the internet is very much interconnected. It's these packets, the data that is sent back and forth from one computer to a server, anywhere, even in the same state. It's going to bounce around through a number of different touch points. And if everywhere, it has to broadcast this information to whoever may want it. Well, it doesn't really make any sense. The more intuitive model, the better model, is to have users subscribe or say that they actually want this data. So, like if you imagine, ESPN will do this kind of live streaming thing where they'll update your browser for every pitch that happens, and it'll tell you if it's a ball or strike, where it was in the strike zone, and in addition to the score, the real-time score. But if you can imagine the noise that would create trying to make that information available to every computer in the world, well, that's not a reliable model. So UDP, if it makes sense at all, it's going to be on some small network. Like if you had a conference or something, then you could kind of do this radio thing, or this unreliable data transfer to computers that are on the same network. But it just turned out to not be a very in-demand model. So the reliable format, the one where you subscribe if you want, and then you get this request reply model, or these acknowledgments for any data that's sent, turned out to be just much more in demand, which is why you hear about TCP IP and not UDP IP or anything else. But the other two protocols, ICMP, again, I don't remember what the acronym stands for, but this is ping. And so it's just a very simple communication protocol. It's, again, request reply. And it's ping pong, right? So you send out this message, you say, hey, is there a computer at this end? And you will typically get a reply. Now, it is possible for that other machine to disable ICMP, so it may actually be on the network exactly where it says it is, but it could be a black hole and it's just swallowing or dropping any inbound communication. And so there are security reasons for doing that. You just may want your machine to be dark. Like if you ever go to a Black Hat conference, you may want your machine to be as invisible as possible to the other individuals on that network. And so, but under normal circumstances, the server or the machine will reply if it's at that particular IP address. And then it's also possible to, I think Traceroute is run using ping or ICMP, but it's been a while. But you can find the hops, the different checkpoints along the way that relay your communications to this other machine. In theory, there's also many ways that breaks as well, but on a friendly network, that it is possible to run that. And then the other one is UGMP, and UGMP is to ICMP as UDP is to TCP, right? So it's this group ICMP thing, and UGMP, to my knowledge, is even less used than UDP. So the two that you're going to want to concern yourself with are TCP and ICMP, or ping, whatever. But TCP, essentially everything you do on the internet, like you have to study computer science to use anything other than TCP, because basically everything is going to go that route. The FTP, the file transfer protocol, the secure file transfer protocol, HTTP and HTTPS, the protocols that's in the hypertext transfer protocols, right? The web lives on, it's on HTTPS now, but it used to be HTTP. And those sit on the application layer of TCP. And so it's all basically TCP, and you can find edge cases for other stuff. So if you're setting up a network, you will use ping, you will use ICMP. But other than those cases, you're basically living with TCP, right? So whenever we talk about the internet, we're typically going to talk about TCP IP. And so when I learned it, there were 7 layers, and then years passed, and I forgot all of it. And I looked it back up, and I was like, you know what, 4 layers, that sounds about right as well. So you may see differing documentation, but the gist of it is you have something, you have an application that's generating these web requests. It could be surfing to a website. It could be a game like Minecraft or Fortnite or World of Warcraft or whatever, something that's communicating to some other server or service, whatever. But something is generating the requests, and then the application makes that request, and then the operating system does the bulk of the work, and it breaks down the request so that into TCP requests, right? So okay, so we'll talk about how HTTPS sits on top of TCP later. It lives in the application layer, but the TCP requests are also doing something similar in that they create these frames, these windows, and so okay, so imagine that you are I was going to say a fish market or something like that, but imagine that your friend is standing 10 feet away, and you say, hey, catch this, and you toss him a package. Well, he's going to yell at you for doing that if you don't give him a heads up. So, what would you ask if you were on the receiving end, right? Like, well, how heavy is it? How big is this package that you want to throw my way? And so that's exactly what happens with TCP. So there's this kind of handshake that happens. There's a synchronization to make sure that the machine actually exists on the other end. There's an acknowledgement from the other machine, and then there's an acknowledgement of the acknowledgement from the original machine. It says, I still want to talk to you, right? And so it's the SYN-ACK, right? And so once that's done, then it kind of handshake, a negotiation goes on and says, okay, well, I would like to send you, some data that's, X number of bytes long. I'm going to break it up into windows, into frames. Let's say we start with something along the size of 1 kilobyte, and if that works out well, then we might increase it up to 32 kilobytes as we increase in speed and so forth. And so, all of this is kind of negotiated up front, and then the data starts going, and you send it one packet at a time, and then like, okay, well, did you get that? Yeah, I got it. Okay, here's the next one, and so forth. And then if that starts working really well, then the receiving machine knows how much data there is to be sent, and so the sending machine, confident that it's already arranged this with the other end, on the other end of the communication, it just starts numbering the frames, 1, 2, 3, 4, and so forth. And so the frame, these windows or whatever, are labeled with these serial numbers, and they're just sent. And then as it gets the responses, it kind of checks them off. And if a frame arrives out of order, then the receiving machine will communicate back. It's like, hey, I'm missing, frame number 1204 or something like that. Could you resend it? And then the sender will, the sending machine, the originating machine will send that, and so forth, right? And so that's kind of what's going on at the transport layer. And so but that is handled by the operating system, right? And then the internet layer is the network card and so forth. So this is the point where the machine touches the network, basically. And so that is in itself a communication. So we're familiar with like the high-low voltage concept. 1 is high and 0 is low. But it's important to note that 0 is not 0 volts, right? So as it's sending these ones and zeros, there's so in order to send something at 100 megabits per second or whatever, you divide the second up into 100 million parts, or thereabouts, and so that's the length of a transmission, and then for however long that time is, you send either the low voltage signal or the high voltage signal, but not 0 volts, right? So you're still communicating something with low voltage, saying, okay, well, this is 0, as opposed to my machine is dead, this transmission is over, right? So 0 volts is never something that's sent, right? And so the modems, the modulators and demodulators, are jumping between the high, the modulated state, and low, the demodulated state, right, in order to communicate these ones and zeros. And so now we use network cards, which essentially do the same thing, but it's significantly faster than the old modems. Okay, so that's happening, and that's where the machine touches the network, and that's the internet layer. And then the link layer. And so the link is all of the hops that are necessary, right? So I believe that the actual Ethernet cables themselves, or the Wi-Fi layers, as well, would constitute the link layer. And so in order for this communication to happen, you're running kind of a relay race. And so your machine is the first one to hand off the baton, and then the baton gets handed off to from your machine to your router, from your router to your internet service provider, from the internet service provider to some higher level connection, and then it gets routed based on routing tables to wherever that destination IP is. And so it's running this relay race. It hops along, and so that's the link layer. And so we'll talk about hubs and switches and routers here in just a second. But okay, so the main concept is that there's different layers that have different responsibilities, all to just transmit this data from web browser to server and then back, right? And so it is a stack, right? And we talked about the stack of plates or whatever before. So the lowest layer in the stack is the application, and then the transport protocol, and then the internet layer, right? So going through the network card, and then the links themselves. So the stack gets built, and at the top level is the link, and so the links are passing it along, and it has a time to live. And so each time the baton is handed off, there's kind of this tally that gets counted up, and it says, okay, well, if it takes more than 32 handoffs, the thing is impossibly far away. We're not going to deliver it, right? And so that's what the TTL is. And so that gets tallied as well, and that happens in the link layer, right? And so it finds its destination, and so that outer packaging comes off, and we get to the lower level in the stack. So we've popped off that from the stack, and then we're at the internet layer. So it goes through the network card, and that layer gets popped off, and then we're at the transport layer, and so we test, we make sure, we I don't think we use Hamming code words anymore, but we do our cyclic redundancy check or whatever parity check it is to make sure that the data came through unadulterated. And so that happens at the transport layer, and like, okay, well, the data was reliably delivered. We received it without error, and so the transport layer envelope comes off, and then we've reached the innermost of our Marushka dolls in the application layer, and so it gets processed by the server at that point, right? So we're talking about reliable, unreliable. We talked about the TCP/IP stack. Okay, so the next is DNS and address resolution. Okay. So the domain name service, it changes the address from google.com or youtube.com or facebook.com or twitter.com or whatever into an IP address, and the IP address is used in routing. The address resolution protocol from within a network. The computers communicate using the media access control addresses or MAC addresses, or I always call them machine addresses, and so it's a serial number essentially programmed into your network card, into your network interface card, and so it's the physical address of that card on the network, and so. This is a little bit like social security numbers versus address, right? So if you are a citizen of the United States and you have a home, then you have both a home address and a social security number, and so the social security number follows you wherever you live, right? And that's the equivalent of the machine address for the network card, but your home address is just wherever you are, at that point in time, and that's the IP address basically. And so whenever a switch is relaying your packets, it does it by your machine address, by the MAC address, or in this analogy, your social security address, to make sure that it delivers it to the proper individual, rather than using the IP address. And so, I talked about, I said that I would inform you of the network security implications of all of this along the way. And so, essentially what happens is whenever you connect to a network, if the router for your network is the one that's assigning IPs, it's dynamically assigning IPs for the network, or that subnet or whatever. Then the machine connects. It looks for the default gateway. So the link, the hop or whatever that gets it out of there, right? So this is the equivalent of the neighborhood mailbox or whatever. So it looks for that and says, okay, I need you, default gateway, to assign me an IP address for this network. And so the gateway, which is keeping track of these things, is like, okay, well, I've already assigned all of these other addresses, so you can have 192.168.0.115. Go for it. That's your IP address. And so the computer, it rejoices. It's like, hey, I have an IP address. Let me tell everyone on this network who I am and where I live, right? And so it, unlike in real life where you never really want to divulge your social security number, it goes out and it says, okay, so this is my MAC address, this is my machine address. You can find me at this IP. And it does this using something called the Address Resolution Protocol, the ARP protocol, right? And so we just take this at its words. Like, okay, that machine says it's this person, or it's got this MAC address. That's perfectly valid. Go ahead. So this is where the security aspect comes in. So it's entirely possible for another machine on the network, a malicious machine, to say, hey, no, that machine address is now located at this IP, right? Because we didn't do any form of validation. We just trusted that the machine was who it said it was, right? And so this is known as Arp poisoning. So you tell the rest of the network that you are this machine, and so either it will overwrite the previous machine, or it will update its IP tables to indicate that that machine address lives at both addresses, and any communication that comes in, it'll forward it to both. So this is the equivalent of just getting a copy of your neighbor's mail every time that something comes in from the router, right? So this is where part of why encryption is so important. So there's nothing to stop other machines on the network from listening into your traffic. So it's very important that you communicate your data over encrypted channels. So all of that to say, right? So DNS tables map and DNS servers or whatever, they map common names like google.com to IP addresses, either IPv4, which is that 192.168.0.115 address, or IPv6, which is something of this form, right? And so to my knowledge, IPv6 is not universally implemented just yet, but I think everyone can agree that it would be really nice if we could go to IPv6 because it supports more addresses, right? So instead of 2 to the 32, I believe it's 2 to the 64 addresses, which is more than twice as many. It is 4 billion times as many as currently supported. So it's a significant jump. And I think at the time that IPv4 was implemented, everyone thought that 4 billion connected addresses was a far-fetched idea, and now it is very constrained. And so the way we work around that is through network address translation, which we'll discuss in a little bit. But okay, to review, DNS tables map from google.com to IP address, and ARP tables, address resolution protocol tables, map from IP address to machine address. And ARP poisoning is the sticking it to the man of this protocol, right? So it is possible to have a malicious machine on your network listening in to all transactions, right? So that is the importance of having a good security key for your network, for your wireless network, and for encrypting your data for anything that you send out or receive on your machine. Okay, so hubs, switches, and routers. So there are wireless routers, but when I discuss these, I'll talk about like physical connections, right? So a hub is essentially a town crier. If a machine, sends a packet over a hub, every device connected to that hub is going to receive the same message, and it doesn't really distinguish. It makes no attempt to figure out who it's actually intended for. A switch will rely on the machine address mappings to specifically forward the incoming packet to the outbound packet. And so for this reason, because it's not blasting it to every node that's connected to it, a 10100 switch will be faster than a 10100 hub. A router is a gateway, essentially. So the router acts to bridge the local network, your home network, to the wider area network, the WAN. And so whenever so if you make a request to Facebook or whatever, then the router will actually repackage your TCP messages or whatever to give its own the external IP address that it has, so that Facebook can send its reply back, because the 192.168 number or whatever, that's designated for local addresses, and so the IP address that you have on your home network, it means nothing to the wider area network. So you need to have it rebranded, and the analogy I have here is sort of like if you're in a multi-tenant building. So if you're working for a company that's on the 15th floor, in suite 1503 or whatever, then you have to not just include the building address, you have to include the suite address as well, right? And so the router is essentially the mail room for that office building. So it receives all of the mail, and then it actually does the additional work of getting it to the right location. And then any mail that's outbound from it, you could say in this analogy, then the mail room would be slapping the return address of the building onto it, and then dealing with whenever it comes back in, right? Okay, so to repeat, the hubs are town criers. They are the cheapest and also the least helpful of these connecting devices, these linking devices. Switches, which are the more intelligent version, and they use the machine addresses to properly deliver the packets, and then routers, which act as gateways to larger networks. Okay, network address translation. So that was kind of what I was explaining. So we just discussed that a router will perform this function of creating a subnetwork and then delivering it to that. And so if you okay, so we talked about 192.168. Whatever, representing some local network. So 192.168.255.255, it'll broadcast the message to every node that's connected to that subnet, right? So that's kind of a reserved address, and then the gateway itself will typically be at something like 192.168.0.1 or .1.1 or something like that. And so it's also reserved on the lower end, and I don't think .0.0 is valid either. So there's a few addresses that you can't use, but aside from that, there's like another 250 up to 65,000 usable addresses with just those last 2 bytes, right? So one external address can map to 65,000 additional addresses on that subnet, right? And so that's the idea behind network address translation. An internet service provider, like Verizon or Frontier or whatever, it can act as kind of a router. It can do the router services, and then the their customers will connect to them via another protocol, something like point-to-point protocol, PPP or whatever, P2P, something like that. No, it's peer-to-peer, point-to-point protocol, PPP, right? And so it manages that. I'm not overly familiar with the implementation details of PPP, but essentially the ISP then acts as a router, and it stamps its external internet address, its external IP address to any of its customers' communications, and then it does the mailroom thing for the responses, and so it's via network address translation that we're able to connect more than the predicted 4 billion device limit for IPv4, but IPv6 would still be really nice, especially with smart devices on their way, right? Like, even though my fridge doesn't necessarily need to do anything on the internet, apparently we need to make sure that my future fridge will have that option of connecting to the internet to I guess get the weather or whatever. So okay, anyway, so yeah, network NAT translation or network address translation is just basically using a router to connect multiple devices to some external network, to the wider area network. Okay. Okay, so encryption and security. So we talked about Arp poisoning and how it's possible for a malicious machine that's on the same network to listen to the traffic that's coming through. And so that can be beaten if whatever it's receiving is encrypted, if it is itself encrypted. So how do we achieve such a fantastic result? Okay, so for our purposes, there's I mean, there really are just two types of encryption. There's symmetric encryption and asymmetric encryption, and I guess anything else would not be considered encryption because you couldn't really decrypt it, right? Okay, so symmetric encryption is whenever you use the same key to both encrypt the data and decrypt it. So in order to create your ciphertext, and then in order to undo it. And asymmetric encryption, which I was extremely skeptical of whenever I was an undergraduate. I didn't understand how it was possible. But you use a different key to encrypt the text than you use to decrypt it. And so this relies on modular arithmetic and some concepts from abstract algebra. And yes, I have since come around to the idea that it is both possible and widely used, right? But yeah, it's definitely a foreign concept. I think whenever you think of encryption, you think of this type of encryption that we encounter whenever we're kids, where you make a substitution or something, or like, I mean, you could consider Pig Latin to be a form of encryption as well, right? And so, it's really simple and really easy to undo, especially once you understand the rules. But asymmetric encryption has the advantage that you don't have to agree on what those rules are up front. You don't have to agree on or you don't have to agree on a password or on a key up front. So that's exactly the idea behind public key encryption. So a website or whoever, they can make their public key publicly available. They can just put it out there, and anyone that wants to communicate with that website can download their SSL certificate, their public key. They can use it to encrypt a really small message, something that's on the order of like 1 kilobyte, to make a request. And so typically what they'll do is whenever you make that request, you will send you will generate a symmetric key, something like an AES key, and you'll send that as your encrypted text. And then you need the private key in order to decrypt that message. So only the provider of that certificate, the verified entity, will be able to decrypt it. And so once at that point, both of these parties will have agreed on this key in order to encrypt and decrypt the data, and then you can use other algorithms to do it. But it's kind of this marvelous innovation that the RSA guys came up with to create asymmetric encryption, and so that allows internet traffic as we know it, and so I think it's just absolutely brilliant. We'll go over that a little later in the semester, but it's just it's really cool. Okay, so hashing algorithm. This is a bit like if okay, so whenever a car comes off the assembly line of any motor company, it's essentially identical, and so a hashing algorithm is a little bit like those I forget the name or whatever, but the car crunchers, right? So you crush the car or whatever, and if the input is identical, right? So if it's the same model car, then the crushed version of that car will be identical to the other crushed version, right? And so yeah, that's essentially what a hashing algorithm is doing. It's mapping identical input to identical output, and if it varies at all, then you get something dramatically different. So like if you change the engine in one of these cars, then the oil stain pattern or whatever that's under that comes up on the crumpled hood will look a little different, right? And so that's the idea of hashing. But the results are more dramatic than the car crusher would provide. And so, but there are limitations to the hashing algorithm. So a 512-bit algorithm like SHA-512 or SHA-2, I think it's called, would only be able to represent 2 to the 512 unique values. Now that is a pretty significant number, but that's less than the number of distinct possibilities of 1 kilobyte binary file, right? So something that is 2 to the 1024 bits, or possible values, right? So a 1024 bit representation, right, in binary would be able to outperform that. Now, in reality, with text, right, with ASCII text and so forth, you're only using a really small subset of the possible representations. But for encrypted text, where it's kind of, it has no real meaning, then it's possible to get repeats. However, there are different hashing algorithms, and if you use the panel, if you get like 5 different hashing algorithms and they all agree in output value for a given input file, then you can believe the authenticity of the file that you've downloaded if it matches those other 5 files, right? So even though hashing algorithms can't necessarily guarantee 100% that the file is authentic, it's pretty reliable that if the file size matches and the hash matches, and the program is at all executable if it was a binary file, or readable if it is a text file, then you can pretty reasonably assume that it's the original file. Additionally, if you combine it with other hashing algorithms and they all agree, then you've got what you were looking for. Okay, so back to asymmetric encryption and SSL certificates. Okay, so whenever you install an operating system on a machine, it comes preloaded with root certificate authorities, trusted root certificate authorities. So on Windows, through the Microsoft Management Console, it's possible to add a plugin. You just double-click on certificates and it brings it over. And you click OK, you select My Computer, click OK. And then you go to Trusted Root Certificate Authorities and then Certificates. And you can see the public key for these root certificate authorities that are here, right? So we all have to believe something at our core. And Windows, Linux, and Mac, they all have these pre-installed root certificate authorities. And they say, okay, well, if there is a chain tracing back to one of these root certificate authorities that says that this certificate is valid, then I can believe that the person on the other end or the entity on the other end of this communication is who they say they are, right? It is possible to generate your own root certificate authority and install it on your machine or the machines on your network, and then you can issue your own certificates, and you don't have to necessarily pay to get them, right? Like it's possible using OpenSSL, and if we have some extra class time throughout the semester, maybe I'll do a video lecture on that so that you can go through that process. Okay, so the SSL certificate is the public key, right? And so earlier, just a few minutes ago, we discussed how it's possible for someone to visit your website, download your public key, encrypt a message, and send it to you that only you, with the private key associated to that public key, can possibly read. Okay? Back to network security. How do we beat this? How do we cheat this fact or whatever? Okay, so now we're going to discuss something that's called a man-in-the-middle attack. And so the idea is that it's the computer version of a con man, basically, right? So, imagine you have a guy that goes door to door, right? And he pretends to be from a bank or something like that. You give him, he convinces you to trust him. He signs you up at a bank. He can provide the bank's statements and so forth, but he's acting as this go-between. But in reality, what's happened with this con man is that he's used your information to gain access to your personal records or your personal data, and then he has used his own signature at the bank to open up the account, so that as you put money into it, he can eventually close out that account using his own signature or whatever, right? Like that's the idea behind a man-in-the-middle account, is that if you are not directly communicating with the entity of authority, right? In this case, a bank, or in the web version, Google or Facebook or whatever, then you're at risk. Then someone that's the go-between can actually listen in on all of your communication. One of the reasons that it's so important not to get a virus installed on your machine, or have a worm take over your machine or whatever, right? To protect the integrity of your machine, is that if someone installs their own root certificate authority or their own trusted certificate authority on your machine, and then they act as this go-between, and so they issue their own certificate saying that, yes, I am Google or I am Facebook or whatever, and because it is trusted on your machine, because you gave that individual access to your machine either through getting hacked or through some act of social engineering or whatever. This is why you lock your machine, right? Maybe you just went to the bathroom and you came back and they had already done the work, right? And so then they can act as this in between, right? And we've already shown or discussed how if they're on the same network, they can pretend to be you. And so then all of your communication gets routed through them. They, having the trusted certificate or whatever, they decrypt your data, right? They perform the exact same actions with the entity you're trying to connect to and say that they are you, and then they just forward the data back and forth, but they're sitting in between, and at any point that they choose, like once you've sent your password or whatever, then they don't need you anymore, right? And you log off, you go do whatever, and they can now authenticate as you and perform all of those trusted operations that are really designated for you. So it is the reason why you need to take care to have a strong password, for accessing your machine, that you lock it whenever you're not using it, and so forth. Is because it's entirely possible for some malicious user with sufficient knowledge, with not much more experience than you have right now, just 3 lectures into this class, to do whatever they want with your data, if you're careless with it, right? Okay, so that's the role that SSL certificates play. That's how you can beat it. They essentially act as this handshake, this trustworthy handshake that allow clients like web browsers to establish the key for a stream cipher, so like AES, which we'll discuss in a minute, and then they communicate using that new that lighter weight encryption. So it's basically just for a handshake or whatever, but there's very significant applications or implications if your machine gets hacked and the other individual is sufficiently malicious. So do lock your computers whenever you're not using them, right? Okay. Okay, so symmetric encryption and diffusion of information. So as we discussed earlier, symmetric encryption, it doesn't guarantee a standard necessarily of quality for the encryption. It just means that you're using the same key to encrypt and decrypt the data. And so the simplest form, the one that we probably all learned first, is a substitution cipher. So you replace the letter, like you write a letter to a friend and then you encrypt it. You go through, and everywhere that you previously wrote the letter A, now you write the letter X. If you previously wrote B, now you write the letter K. If you wrote C, now you write the letter A, or something like that. And then in the end, you've replaced all 26 letters with 26 substitutes. And then your friend who has that key, they go back and they undo that substitution, and they're able to find the original message. And it's really cool whenever you're a kid. It's the coolest thing ever, because like you can write something that your parents can't decrypt or whatever. Okay, so if the information's important enough and someone wants it badly enough, then they're going to find a way to get it. So let's say you're trying to transmit military information over this. Well, someone on the other end is going to eventually receive the cipher text. They're going to receive the encrypted message. And if it's something as simple as a substitution cipher, they're going to use known methods in order to break it. And so in this case, every language, certainly every language that uses the Latin alphabet, has an affinity for letters, right? So in English, the letter E is our most favored letter. It's the most common letter in the dictionary or whatever. And then it's followed up with other letters, and they're used at a rate, at a frequency. And that frequency is kind of like it is built into the language. And so if you analyzed the encrypted message and then you replaced each letter with the associated frequency, then after a few tries, so the first letter you would get is E, like you would break that one pretty easily, and then you just have to get the other 25 letters or 25 substitutions, and you would just replace them by frequency. So the letter X now occurs with this frequency, and so I think that one is A, and so forth, right? And then after not very long, you've broken the cipher, and so this is kind of built into Wheel of Fortune fans. Pat Sajak will always guess RSTLNE whenever they do the bonus round. And the reason that he's guessing those is those are the most frequently used consonants, and the letter E, the most frequently used vowel and overall letter, to try and help the player along. But that familiarity that we have an affinity towards certain letters, is well known to every Wheel of Fortune fan. So, okay. So if that cipher is terrible, then what's a good one? Well, in the 80s, I guess, they were using the data encryption standard, and I guess the early 90s. And then they hardened that to triple DES, and then it was realized that even that wasn't strong enough. So the Department of Defense kind of had this worldwide contest for a new encryption standard, and I think they received 6 submissions, which is, it blows my mind that you have this global competition and you only get 6 responses. But maybe that was just 6 serious responses. And so, each of them were considered, and AES was originally thought to be a little too simple, but as they analyzed it, as the experts analyzed it, they realized that it is just a fantastic algorithm. And so, earlier we were discussing how TCP kind of breaks up the data so that it can send it over the wire and so forth. And so at the application level, AES does the same thing. And so it breaks the message up into blocks of 16, and if it's smaller than 16, then it'll pad the end with zeros or whatever, right? So you get only blocks of 16 bytes. And so it's a 4x4 array, and then it goes through and it let's see. So first it performs a substitution. So we said the substitution cipher is kind of weak, and it's easily broken. But as part of a more complex algorithm, like it's just one of 4 steps, is actually a good inclusion, right? So it performs a substitution, and then it performs a permutation on the rows, and then it takes the columns and it performs an XOR operation on them, right? So it takes the first column and then it XORs the other rows by it. I think it XORs the second row by the first, and then the third by the second, and the fourth by the third, and so forth, so that it's kind of jumbling up the data. And then it takes the encryption key and it uses that, and it performs another XOR operation row by row, I think. I can't remember exactly, but it does it, right? And then it goes back and it repeats. It performs a substitution, and then it shuffles the rows, and then it does the column operation, and then the key again. And it loops through this, and depending on the key size, which is either 128 bits, 192 bits, or 256 bits, for the smallest key size, it does it 10 times, for the medium 12, and for the largest 14. And so, but every one of these operations is invertible, so that you get the encryption data, and it's just noise. If you look at it, you could spit out the binary numbers, and it, however regular the input, the output is just entirely noise. And then it is invertible, though, right? Through the exact same process, you just perform the reverse operations, or in certain cases, the encrypted data is something regular, like a counter or something like that, and you perform an XOR operation with the clear text data, and that is sufficient to encrypt it, and so that you're performing the encryption operation even whenever you're decrypting, because the XOR is its own inverse, right? Like we might discuss that later, right? But the exclusive OR operation, if you're not familiar with that, the byte arithmetic of the XOR operation, you might want to take a minute or two to look over it. Okay, or bitwise arithmetic of that. Okay, so that's AES, and that's the symmetric encryption or whatever. And at present, there is it's hardened. It's perfectly secure. There is no known way to beat it. The only chance really is if the key gets leaked somehow. But if you don't have the key, you're not going to be able to decrypt AES encrypted data for many thousands, thousands or tens of thousands of years. So it's considered secure. Okay. So code signing. Okay, so earlier we discussed hashing algorithms, and so code signing is kind of something similar. So you take an RSA private key, and you use that in conjunction with an RSA hashing function, and you feed into it some binary file, right? In this case, like an exe or some executable file, or the entire app directory, I think, in Mac application, or just the binary file in Linux, right? You feed that in as input, and you have the private key, and the hashing algorithm munches it up and performs whatever operation with this key, and it gets some value, some output value, right? Just like a normal hashing function would. And so it stamps that onto the application. And so the application gets deployed and gets downloaded in Windows or Mac, and in theory on Linux as well. But Linux doesn't have the stop operation or whatever. So it doesn't check whether or not an application has been properly signed, and it doesn't do anything if it hasn't, right? So in Linux, you're kind of expected to check the hashing, the hash of the source code, or the binary file that you've downloaded or whatever. And if that doesn't match, then don't install it. They expect you to do a little more on your own. But on Windows, they have the no execute bit or whatever that they take advantage on the processor, and on Mac the same thing basically. And so the idea is that the operating system will check against the public key. So in this case, you're using the private key to essentially encrypt or embed some information into this output, and then the public key is able to verify that based on the input, that it matches what is stamped onto the program for the output, and so it's able to tell that the program was built and signed by the same person that holds the private key for the published certificate, right? So that's the idea behind code signing. It's not so you have to use it for Mac. It is optional for Windows, and it's totally ignored on Linux. But I do expect it to grow in popularity going forward. So just be aware that that's kind of what's happening, is that code signing is just a way to verify that the program was built and published by the person that claims to have built and published it. Okay. So if you write a successful application or website or whatever, then you're going to have to deal with scalability. So I think last time I'd mentioned that it basically doesn't matter how poorly written your code is. If there's only one user, then it can be total garbage essentially, and it'll still work reasonably well, right? Because nothing is really stressing it out. It hasn't really run into any kind of demanding activity. But once you deploy it, you have to make sure that it's written in such a way that it can be broken apart, that it can be handled by independent services that are not in communication with each other, and that it continues to be responsive. And so that in itself, that is the job, basically. That is so I remember when I graduated and I thought, okay, well, what happens whenever I write an application and it works? Like, does that mean that I'm out of a job? And essentially, no, and especially with the internet, because the user base is constantly growing in theory, right? And so you write the application, it works, it gets deployed, and then hopefully, if it's successful, it gets adopted. And as it gets adopted, more and more people are using it at the same time. And what was previously working, what was well written and well thought out and tested and everything, starts breaking, and it breaks for different reasons. It breaks because too many people are using it simultaneously, or trying to access the same data, or trying to write to the same location, or whatever. And so the job, the discipline is finding ways to respond to these demands. And so you have to do it pretty quickly, because think of your own experience in using websites. If it doesn't work, the tendency is to give up on it pretty quickly. And so that is kind of what we hope to understand in this class, and that's kind of the math around this, is understanding, well, how long can I expect this thing that was well written to work before I have to come up with an even more clever solution to keep it working for a larger user base. Okay, so dealing with really large numbers. So in terms of services or APIs, or web APIs, the prescribed method here is to go stateless. So it is possible through reverse proxies like Nginx and so forth to maintain a session, and if a request comes in from the same user, that the same user always gets mapped to the same machine. But that creates a little bit of overhead at the inbound point. So it's typically better to just treat things in a round robin fashion, or to have that same service, Nginx as a reverse proxy, to use something like responsiveness. So whichever server is performing the best, is responding quickest, should handle more and more requests, and then it's kind of balancing the load in that regard. That way, if one server is asked to do something that's a little more intensive than another server, that it still gets balanced in something of a fair method, right? Or you can just do straight round robin, where each request just goes to the next server. But in order to do any of these, you need to write your application in a way that any server can respond to any request, and it's a different way of thinking to go stateless, so that it's not this ongoing communication between the same server and the client, that it can constantly be handed off without loss of anything, right? And so that's something that you have to build into your client and server application. So you have to take that into account, that it's not going to be this running dialogue like you would have with your counselor or your advisor or whatever. It's a different. It's more like writing into the IT department or whatever, where you submit a ticket and whoever gets to it gets to it. Right? Okay. The orders of magnitude. Okay, so again, at a really small scale, if your program is simple enough, then it's entirely possible to have it live entirely on the processor. So modern processors have, I think, like 2 megabytes of L3 cache, or like 512 kilobytes of L2 cache or whatever. So if your program is only a couple hundred bytes, then it doesn't even need RAM. Whenever it's loaded, it can load entirely into the processor, and it'll be lightning quick, but you're not going to be able to do anything complex in that amount of space. So if you have to move from on-die storage, from the processor to RAM, then you get enormous gains. So my desktop has 32 gigabytes of RAM, which is way more than the 2 megabytes I just mentioned for the processor. But it's 10 times slower than if it was all loaded onto the processor, which is acceptable. RAM is still pretty quick. That's not too bad. I'll take the 10 times hit. But if your program scales even further, then it's going to be swapped in and out of virtual memory, and we talked about thrashing a little bit last time. And so there's a little bit of overhead in moving it back and forth. And additionally, every time you can expect it to be 10 times slower accessing data from the hard drive than from memory. So it's always tempting whenever loading data from cold storage or even from hot storage like a hard drive or whatever, to load it all into RAM, but you have a finite amount of RAM, and if you exceed that, it's still going back onto the hard drive. So you have to be intelligent in how you do that and judicious and so forth. But it's another hit of a factor of 10 to go onto RAM. If you're loading from a CD drive or the slower USB drives, USB sticks have gotten wicked fast, then it's an additional hit of a factor of 10 to get data off of there, or alternatively to get data from somewhere else on the network, because of all of those hops and all of the overhead of the Marushka stack of the Russian doll stack of the TCP/IP communications, right? And so it's you can expect it to be 10 times slower than accessing the hard drive on the same machine, the same server, desktop, whatever, to go onto the network and retrieve it, or to go into the cloud just as well, right? Like it's still going through a series of hops, and there's the overhead of network communication. And so each time you reach further and further away from the processor, it tends to add about a factor of 10 in terms of cost. And so that can add up pretty quickly. And so, it on one hand, it's basically unavoidable that you're going to have to store stuff on the hard drive or on a network if your program is big enough. And so the job then becomes finding ways to optimize this, to keep it quick and keep it responsive. But just keep that in mind, that each time you have to reach further and further, it's about 10 times slower than what you were previously using. Okay. So finally, practice. I love this job. I've been doing it for 15 years. I still love writing code. There are a few things as satisfying in life as writing something and having it do exactly what you had in mind. It's a great feeling. At first, it's really hard to come by. The first program I ever wrote, or first successful program, was it was a simple program, and it computed quarterback rating. So for like NFL quarterbacks. And so the algorithm is really not that difficult. So for passer rating, it takes into account the rate that a quarterback throws touchdowns, the rate that they throw interceptions, the yards per attempt, and completion percentage. Maybe I don't remember the last one, but there were 4 inputs. And then it took those inputs and spit it out whenever it matched what the newspaper said for a given quarterback stats. I was overjoyed, right? And so, there's no demand for it. There's no monetary value in it or anything, but it worked, and it was mine. It was something I came up with, and that was the first time that I really experienced that joy of devising something and then creating it and watching it come together. And so as we go along, hopefully I'll be able to come up with some examples that those of you that are interested can follow along and do at home, and hopefully it'll inspire you to come up with something of your own that's a variation of the tricks that I'll show you, or whatever, and you can create your own thing, and you'll get that feeling, and you'll be on your way. But it's very important that you code as you go along, And so even though I'd had a little bit of experience, with that success as an undergraduate, I still felt very overwhelmed whenever I got my first job. I felt like I just didn't know enough to really be drawing a paycheck or anything. And so it was a really uncomfortable feeling. So I will do what I can to prepare you now to avoid that feeling later. But the best advice that I can give you is to just practice as you go along. So more than the assignments you get, hopefully you can find something within computer science or software development that you really enjoy working on, and that you're willing to do in your spare time, so that you can advertise that in yourself whenever you're interviewing for your first job, and that you'll enjoy doing and continuing to do once you get that first job. But in order to practice, I think it's important to avoid the frustration of having something that works and works and works, and then, oh no, I totally broke it. What did I do? How do I get it back to working? I don't remember where I made the changes, and so forth. And so this is where source control comes in. And so it's worth, it can be a little tedious, but it's definitely worth it. The typical pattern is that you have some trunk or main branch that you work off of. You want to add some new feature, so you create a new branch based off of that trunk or main branch, and you work on it. Every day that you work on it, it shouldn't be a big deal for your code to compile, right? Like everyone has broken a build before, but you never want to get so far between compilations that you don't really know how to get it to compile. Like that's kind of bad. So never check in something that won't build, and even if you have to lose a day's work, it's better than spending a day trying to get it to build again, right? So if at the end of the day you can't get it to build in less than 10 minutes, then just throw away that day's work. It probably wasn't very good if it doesn't even build, right? But if it does work, if it does build, even if it doesn't work the way it's designed or intended, or if it's not fully implemented, check it in, and then once you've completed your feature and everything's built, then you merge it back into the main branch. And so it's really tedious. It's really easy just to maintain that main branch and continue your daily check-ins or whatever. But whenever I think at your stage in the process, it's really important to develop good habits that'll allow you to work on a development team once you find a job. And so I think for that reason, whether you're using Subversion or GitHub or whatever, that you follow a process very similar to this. And then in doing so and developing good habits, I think it's very important that we never check in code that does not compile. Never. It has no value to check in code ever if it does not compile. It doesn't matter what brilliance you think is in there. You can make a note if you have some really clever comment or something, copy it, save it somewhere else or whatever. But don't check in that code. If it doesn't compile, it's no good to anyone. Right? Okay. Project management. So there's software like Jira or Monday.com or whatever that you can find that will track progress on a project. And so essentially, a project is just a collection of features, or if you're using Scrum or Agile or whatever, then you're writing these user stories. So my application should allow me to log in, or something like that, right? And so that becomes this item of work to be done. And so it's tracked in project management software. It's also possible to just use sticky notes and be like, create login feature or whatever. And then you just have these columns and says unassigned, started, completed, or blocked. And then you stick it in the appropriate column. So once you start working on it, it's started. If it's finished, then it's completed. And if there's something that has to be done, like this cannot be completed until we purchase the SSL certificate or whatever, then it goes in blocked. Okay. The automated tests, there's like XUnit for Java, I think, InUnit for .NET, and then Jest and stuff like that for React. And so there's whatever language you're programming in, I can almost guarantee that there is a an automated test runner for that language. And so usually it's the test project is built parallel to as a sibling of the project itself that's actually performing the work. And the unit tests are testing a unit of functionality. And so the example I give is, if you have a function that just squares the input, then you could expect to create 3 tests, right? So you do the positive test, right, to make sure that a valid input will yield a valid result. So it should do what it says, but then it should also break in predictable ways, right? So next you would put in, you'd create a test for the edge case. So if you have a function that squares an integer and returns an integer, then something like 2 to the 31, which is a valid input number, but will result in overflow whenever that square operation is actually performed, you should have it return some predictable exception, right? Like argument out of range exception. So you should understand what the limits of valid input, or what your function can handle, will be. So either you want to change your function to return a long, so accept an int and return a long int, so take in a 32-bit number and return a 64-bit number, or you want to throw an exception, but you need to test that edge case to make sure that overflow is handled in an acceptable manner. And then you also want to test for invalid input. So if I pass in not a number, which in C# is an integer, int.nan, I think, and I think it's also a number in JavaScript as well. And so you want it to throw a predictable exception in those cases as well. And then so the code that you write should break in predictable ways, and the unit test should reflect that. And then it's up to the calling function to make sure that it handles it, that it either doesn't pass in those values, or that it wraps the function call in a try-catch block and handles the exceptions appropriately. But that's the idea behind the unit test, is not just to make sure that it does what it claims, but that it breaks how it should, right? And that the breaking part is really more the discipline of software engineering than the making sure it works part, right? Because that optimism abounds in software engineering, right? But to be a really good developer, you have to make sure that that you are allowing your program to break, and that it is breaking appropriately. Okay. And then brief word on integration tests, right? So integration tests are just automated tests. You might be able to find third-party software. You can write your own software, but it tests that whenever you deploy it, that it is working as deployed, that everything is configured and it's returning an expected result for a fixed input. Right? And then there's load testing, and there is third-party software that will do that. And basically this will just, you can also create your own custom software as well, but to create as many requests as fast as you can, and see how the server or the service that you've deployed holds up against the heavy load. And it doesn't have to work, forever. You just want to get a feel for whether or not you're going to be able to support the number of users that you currently have, and how long you have in terms of growth for your user base before you can expect things to get really hairy. Okay, and then at some point later we'll go over constructing proofs. But I'm a little bit over on my time right now. So, but in order to do the homework, I recommend going to overleaf.com, right? And you can register. I already have a login Right. Right, okay. And then you can create a new project, blank project, whatever. Okay, and then so you have that, and then right, and then you take the main.tech or whatever .tech file, homework1.tech, and you copy and you paste it in, right? And then you press recompile. Okay, and then it will, so it builds for you, and then you go back up. Scroll past that. Put in your name, so you replace student name with Jane Rowe. You can recompile if you want, and you'll see it pop up over here. And then, oh, I have the answer here. Okay, well, whatever. And then you input your answer here, and you do that for each of the problems. Yeah, you can look up the begin, align. You can wrap these in paragraphs. It's up to you. So the dollar signs are inline math mode. So if you want the text, like just the normal text, to include it, then you'll use dollar signs. If you want the math to show up on a different line, kind of like this, then you'll either use begin align or you'll use something like that. The backslash square, open square bracket, and then backslash close square bracket. And just for your own note, right, like it is pretty easy to break it. So if you don't put anything in there, then you'll get an error. I don't know if it shows it or not. Yeah, maybe. Anyway, so just if you do that, whenever, and you just need a placeholder, just stick something in there and then replace it with the actual values that you want. But overleaf.com is the site that I'm recommending for this. So you just copy and paste the tech contents, the main.tech or whatever, and then you go from there. Okay, so good luck with the homework, everyone, and hopefully this has been pretty helpful to go over all of this review stuff. And then next time I will I will lecture over the stuff that I'm giving you homework on now. I don't think this first assignment is too terribly difficult, so hopefully y'all will do just fine with it. So all right, I will talk to you all on Thursday.